All right, thank you for all being here tonight. Let's get going here. So same set of slides you see pretty much every month at this point. You could probably recite them with me at this point. So anyway, so for those in the room and for those on Zoom, and we do have people on Zoom here tonight, we thanks for being here with us. As always, I say it every week, we hope you enjoy yourselves. We hope you learn something interesting tonight. We hope you make a new friend, and we hope you can reconnect with some of your old friends as well. So thanks you for all being here. Quick cell phone reminder, which I'm going to take my own advice here. All right, I took my own advice, and we're now on stun on my cell phone. All right, any visitors here tonight? Anybody here new visiting? Oh, we got a couple here. Well, we're going to give you a microphone. Just introduce yourselves to us real quickly. And what we need you to do is basically follow the directions on the screen. So it should be easy.
Kevin and Andy Healy. We've known about EVAC for years. I attended a meeting about 15 years ago. In those 15 years, I've been astronomy faculty over at Mesa Community College. Heard about the speaker this evening and figured I'd turn up. And my astronomy experience goes back to being about 5 years old and finger painting Saturn and things like that.
Let's see. Yeah, I've got stars for earrings. I've been a volunteer at Mesa Community College's public night, astronomy night, for at least 10 years. And I'm planning on majoring in astrophysics next year out of state.
Okay. And do you fingerprint Jupiter? Fingerprint Jupiter at all? No. Okay. All right. So anyway. All right. Well, thank you. Anybody else here tonight new? Okay. One more.
Hi, I'm Beverly, and I had a Orion telescope once, but now it's a little easier to handle the binoculars. But I'm a physicist, which is close enough for astronomy experience, I think. I've always been kind of interested in astronomy and planets and stuff, so thank you.
Okay, thank you. Welcome. Well, thank you for being here tonight. We appreciate that. All right. Oh, by the way, there's the comet for those of you who haven't yet seen it. So I grabbed a picture off the internet. I've been trying to look at, interesting enough, I could see it off my front porch every night. So my porch faces west, so I've been watching it with binoculars all week. Well, when it's not raining, but anyway. All right, tonight's agenda. So we have just our general announcements. It'll take 5 minutes. I do them every week. So those that are regular will recognize the general announcements. We're going to talk about a little bit about some outreach events. We're going to talk a little bit about the All AZ Star Party that's coming up in just a couple of weeks. I'll give you an update on club elections real quick. I'm going to give you another update and ask some questions about the Christmas dinner sort of thing. And then we'll have another raffle tonight. So we're going to do raffles tonight and then next month as well. And we won't have a meeting in December. So it'll just be this next one. For those with badges, we'll be all set. All right, and then member presentations. Nathan Eskey will be up here. He's going to talk about a new program that's going to be launching here at the club. So he'll talk a little bit about that. We're also going to have James Yoder right here. He's going to talk a little bit about the star party we had up at the Hyman Rim Ranch a few weeks back. Great location, by the way. I had a great time. I got to go there one night myself. We'll do our short 7-inning stretch then. So we get a little social time for 5-10 minutes, 15 maybe. And then our main speaker tonight is actually right there. And Russ, Dr. Russ Genet will actually be talking about, as you can see there, Speckle interferometry of close binary stars, which I don't have a clue what that is. So I'm actually very interested in what Speckle interferometry is. I know what interferometry is, but I've never seen it combined with the word speckle before. So anyway, all right. So there's tonight's agenda. So general announcements, as always, for those that are interested in joining or renewing your membership, you can do it following the directions on our website. So this is just a screen capture from our website. There's at least 3 different ways you can join or renew your membership if necessary. The easiest thing to do is at a meeting, just go back to the back table there where Brooks is sitting, and Brooks will take your money, and if you want a badge, you can buy a badge as well, and he'll get you all set up and you can become a member there, and we appreciate membership. Membership is important because it pays the bills. So it pays for all those snacks on the back table and things like that. So, so those very important is membership. So anyway, take a look at the website. If you want to know what it means to be a member, pretty much you can, there's a PDF on our website as well, talks about what it is to be a member. Also, if you want to find out what's happening here at EVAC, there's at least 4 ways to know. One of the ways is you can subscribe to our email list. It's not a spam generation machine. You'll probably get about maybe a dozen emails a month, most of them about meetings that are happening on meeting reminders. But occasionally we announce things like club elections and stuff on the alias as well. We don't sell your email address to anybody else. We don't make any advertising dollars off of that. So it's perfectly safe to sign up for that and find out what's happening through those announcements. You can also go to our website, and underneath the events and meetings tab there, there is a Google Calendar, and you can look at that calendar and see what events are listed on that calendar as well. And it'll get busier. We are now going into sort of star party, community outreach type season. And so there's going to be a lot more events where we could use a telescope to go to a school or an HOA or a science center or whatever else. Also, you can go out and look at our newsletters. So we send out a newsletter every month, but you can actually look at the current newsletter or any past newsletters as well by going out to news and resources. And if you pull that down, you'll see newsletters there, and you can look at all the newsletters. And there's several articles in there talking about what's going on, among other things. There's also then the Facebook page. So we do have a Facebook page. There's about 1,000 people that are a part of that now, and a lot of announcements go out there about the club, but then other people post anything from their advertising a telescope for sale to, oh, here's the latest pictures I took out of Pick a Post. So a lot of stuff happening out there on the Facebook page. All right, do you need equipment? We have a couple options we provide as a club here. Number one is we have used equipment for sale. We get used equipment all the time. James Yoder here is our properties manager, and he goes through it, makes sure it's at least in reasonable working order. It may not be perfect, but it's reasonable shape. We offer them at deep discounts. And so if you're looking for a telescope but don't have quite enough money to buy one new off the shelf, we can do this, and there's some nice equipment out there. I actually bought a solar scope myself a few months back. And I love my solar scope, and I got it used through James. So anyway, we also have equipment for rent. We have a rental pool as well. James handles that as also. And we can rent everything from, little Dobsonians to full computerized go-to telescopes. We even have one of those little new C-Star devices that are so popular right now. You can rent those, and the rental fees are pretty inexpensive, and it's a nice way to sort of try before you buy is what that is. That way you can say, oh, I like the C-Star, or I like the Dobsonian, or I like the go-to. You can figure out what you like. It's a good way of doing it before you have to go out and spend the bucks. If you'd like to learn more, there's a couple different ways to do this. Also out on our website, underneath news and resources, there's a virtual beginners lab, and every one of those blue boxes, and I think there's 33 of them on this page, brings up some text that tells you about whatever the topic is on the blue box. It's just a nice way to learn some basics of the astronomy quickly. Also, James talked to me earlier this week, and he is looking to run another introductory astronomy class. So if you're interested in an introductory astronomy class, you can sign up with James. James, you want to talk a little bit about it?
Sure. Yeah, so we generally run those on demand. So if I get like 4 or 5 people are interested, it's 5 Zoom meetings and 5 hands-on meetings. You don't have to have equipment. Or if you do, just purchase some equipment or something and want to learn how to use your equipment, then you'll bring those to the labs. So again, there's 5 labs on the weekend, Friday or Saturday night, and then 5 Zoom meetings. And it's very hands-on stuff. It's not theoretical stuff. It's how to use your telescope and magnifications and stuff like that. So if you're interested in it, come talk to me, and then I'll keep a list of how many people are interested. And if we get enough, we'll go ahead and have that. So yeah.
And I think I have one for you already, James. I got an email this afternoon from somebody who says, hey, I'm new to the area. I have a telescope. I don't know how to use it. Can somebody show me how? James. So anyway, I'll give him your direction. All right. Thank you, James. One of our charters, of course, is giving back to the community. So if you'd like to get involved, there's a couple different ways of doing so. Number one, you can volunteer at our observatory. So as most all of you know, we have an observatory just about a 3-minute walk that direction. And every Friday and Saturday night, it's open to the public. And we're always looking for volunteers to kind of manage the crowds, operate the telescope, whatever. So anyway, it's a lot of fun. I've been doing it now, I think a little over 2 years. And it's fun every day, every month it's fun except for probably July and August. Less fun then. It's kind of hot. So anyway, but luckily it's a short night because sun doesn't set for till late and we're only there about an hour. So anyway, but it's a lot of fun. In fact, I did the astronomy day last Saturday. And so a little different. We got to look at the sun for a change instead of the moon or whatever, but it was a lot of fun. We had about 120 people out during the day. Just to look at the sun. And of course, right now, the sun's pretty much at solar max. And so the sun's very interesting to look at right now during the day. Lots of things happening on it. So it's kind of fun. The other way you can get involved is helping us with our public outreach. And so we have star parties, and we're kind of going into the season right now, where we go out to schools, HOAs, science centers, a little bit of everything. Anybody who wants us, basically, we take 1, 2, 3, 6 telescopes, whatever out there, and we basically show the public the sky. And whatever's up that night, that's what we show them. And it's a lot of fun. And if you'd like to join us for that, please do so. You can see there's a place to email to get signed up as a volunteer for that as well. Greco or this, whichever one you do, you can kind of pick and choose your own schedule. So it's not like when you sign up, oh, you have to be there every Friday. No, you can say, I'm working this month, or I'm not working that month, or I'll do these 3 events, but not these other 6. You can kind of pick and choose your schedule to fit your schedule. So anyway, that's very, very good thing to do, a lot of fun. Special announcements. This was the Greco Astronomy Day, just a couple of quick pictures there, just to show you that we did have people, and looks like Bruce is at the front door there, and then got a young man there at the telescope looking at the sun there. So that was a lot of fun. We also had an Apache Junction outreach event as well. So we had a star party. Actually, we've been out there twice, essentially about 4 weeks apart. And so we had a lot of fun out there. We go out to the multi-generational center there in Apache Junction, and we take telescopes out there. We have a really nice time with all those folks out there. A lot of fun. In 2 weeks from tonight, yeah, 2 weeks from tonight. Wow, it's coming up quick. 2 weeks from tonight, we have our all AZ star party. It's our biggest star party of the year. It's out off of Interstate 10 out towards Quartzsite. It's about a 2-hour drive from here. But the wonderful thing about the 2-hour drive is when you get out there, it's black, inky skies. And so we have usually really good seeing out there. It's a lot of fun, and you get to see lots of things. You get to see this really strange thing in the sky called the Milky Way. You really don't see that. It all looks milky around Gilbert. But anyway, it's a lot of fun. We're going to be out there for 2 nights. It'll be a Friday, Saturday night event. You can see a few of the details there. On our website, it has a lot more details, including good driving directions. So a lot of people wonder, well, I'm driving out in the middle of nowhere. How do I not get lost? So, but anyway, you just basically go down Interstate 10, you get off at Harvard Road, or however you say that word. And once you get off on the road, we have good driving directions on our website. But also we put up a little sandwich board signs that have arrows that basically lead you all the way in from the freeway exit all the way to the site. So anyway, if you want to come out, please join us. The porta potties will be on site Thursday, the day before, and they won't be picked up till Thursday, the day after. So I know some of the astrophotographers in here, Leo and some of the other folks tend to stay a little bit later or go in a little bit earlier and try to get a little more astrophotography in out there. So anyway, the restrooms will be out there from a week, Thursday to Thursday. And everything else you pretty much bring on your own. It's BLM land, so there's really nothing out there except coyotes, jackrabbits, sagebrush bushes, lots of rocks. Anyway, you have to bring your water, whatever else. Some people sleep in their cars. Some people bring a tent. Some people just throw a cot next to their car and sleep on a cot. Some people bring RVs and trailers, so it's up to you how you want to do it. I usually just take a tent for the 2 nights I'm out there. So it's a lot of fun. We will have dinner for everybody on Friday night. It is $5 for the dinner, but we'll cook a big dinner and have a big thing. Saturday night, excuse me. Thank you. Saturday night. And I think that's about it. So hopefully lots of folks will go because it's a lot of fun. We have a good time out there as a rule. Club elections. Elections will be happening next month here. So the good news is this. We had 4 open slots and we had 4 people come in volunteer, and each one won. So I think we're good right now. And so we'll introduce those 4 people at the next month's meeting. And you'll basically see a little short bio for each one of them. And if you don't have any objections for any reason, you'll basically raise your hand and say, yep, I'll take that person as a board member or as a secretary or a vice president or whatever. And we're off and running at that point for the next year. So anyway, that's the good news. Let's see. Club member Greco volunteer Christmas dinner. Usually every December, we do a Christmas dinner in this room for all of the people who volunteer at Greco and or are members of the club. It's kind of a thank you. And so it's free. We don't charge anything for that. It comes out of your dues, of course, but we don't charge anything at the event. But anyway, we can't do it this year. Based on the schedule for the lights, the Christmas lights show they do in the park this year, we can't have a dinner in here. So we're not going to have a dinner this year. So what I need to do is ask a question now. I have been talking with ASU over in Tempe, and they have a planetarium over there. They do a 3D sort of laser planetarium show out there. So I have been talking to them with the idea of basically we go in as a club and go and do the planetarium. And then some people said, well, why don't we just bring in pizza and soft drinks as well? And so we'd have pizza, soft drinks, and a planetarium show at ASU. I would like to know how many people would actually be interested in something like that. So I can see a show of hands, so quite a few. Okay. Tentatively save the date. I haven't written it in stone yet because I said I need to talk to you folks tonight, but it looks like it's going to be Saturday, maybe January 25th. And it'll be actually like a 1 o'clock in the afternoon thing. So we'll go out there. It'll be a several-hour event, and they'll basically have pizza, soft drinks out there. We'll do the planetarium show, and then they're also going to give us a tour of other labs and facilities in that building for the first 2 floors. So they'll give us a tour out there of some of their astronomy and science facilities out there. So anyway, okay, I will pursue that then, and hopefully on January 25th, we'll see a bunch of you out there for that. All right, raffle. We have been doing for 2 months now a raffle for everybody who has their badge on tonight. Nobody noticed I don't have my badge on tonight. Nobody noticed that, okay? In my rush to go camping and everything else, I know where my badge is. It's in the tent. It's just not here. So anyway, so I'll wear my badge tonight when I get back from the tent. So anyhow, have James pick the numbers. That way we're double blind.
I got nominated for this.
Yeah. Well, that way you get blamed.
You want me to read it?
Yeah, you do it.
082157.
Oh, Jonathan, okay. All right, let's do the next one.
Ready? 082167.
All right. All right. There you go. There you go. There you go. You're all set. Okay. All right. And one of our members had some commemorative Apollo mugs from Apollo 12 and Apollo 14. And so we are actually going to raffle these off as well. It's a set. Yeah.
Ready? 082153.
1, 5, 3. Oh, okay. Well, you own some commemorative. Oh, there you go. There's 2. Perfect. One for you. One. Yeah. Well, there's no Apollo 13 because it broke. So, okay. So anyway, all right. So that is that. So we'll have one more raffle for badges next month. And then, like I said, we'll be done for the year for that. So I always like doing this. Kind of fun. I love giving money away. I should be Oprah. So anyway, all right. We're going to do member presentations now. And the first one up is actually Nathan. Good thing you're here. So.
Thank you, Steve. Well, good evening. I am proud to present our new program here at EVAC that recognizes our volunteers and hopefully will foster a broadening of our community and outreach efforts. So our president, Steve, and the board at large wanted to put together a volunteer recognition program as it truly speaks to what the club is all about. And we have a constitution and bylaws, and so I'm going to read this verbatim. But the purpose of this organization shall be to further the education of its members and the public in astronomy and related sciences. And so as Steve mentioned, the club really accomplishes this in many ways through these monthly meetings, through the Skywatcher program that Claude runs, through our amazing observatory right out here, through the equipment rentals and classes that James does. But there's also those EVAC outreach star parties and manning DBAC booths. We're pretty, we're everywhere. And it's through our members and through our volunteers that really helps this club thrive and achieve our goals. So I wanted to just briefly touch on some core concepts. So we were very diligent when we crafted this program. We didn't want it to be a joke or too easy to complete. And we wanted there to be significant acknowledgement and reward or recognition to make the journey worth it. So we'll get into the details in a second, but we really didn't want to make it too easy. For our officers and boards, we wanted to make it easy to run and track. And we didn't also want anyone to just be able to jump right to the end. So we're having a hard start date. Nothing historical counts. So starting right after this presentation, the program is active and volunteer points can start to accrue. So let's go over what counts as volunteering. So as mentioned, the EVAC outreach events, the star parties, Steve showed some pictures of an event that we held in Apache Junction, volunteering at our observatory at Greco, presenting at club meetings, leading or assisting an astronomy class, manning an EVAC booth, publishing an article in our newsletter, and officer volunteering. Now you can see those last two, I have some caveats. So for article published in the newsletter, officers are excluded, and for volunteering for an office, you get 1 point. So you signed up for that job and you get recognized for doing that, but after that point, that's your job. And then this is not an exhaustive list. We're running this as a pilot this year. And so if anything else comes up, the board will meet, talk about it, and vote to see if that should also count as volunteering. Then quickly, what would not count as volunteering, monetary and equipment donations, as you're already receiving a tax benefit for that. Private star parties, such as a wedding, where that benefit does not go to the club. Work associated with an official EVAC officer or board position. Again, we volunteered once, we'll get 1 point, but ongoing, that won't count. And then lastly is paid presenters. They are receiving reimbursement and therefore are not volunteering. Although we appreciate their time and the presentations. Okay, so we're going to do a tiered structure, and we came up with some fun names to go along with the program. So our first tier is called the Stargazer level, and it's going to require 10 volunteer events in order to achieve this. So as part of this, you'll receive a certificate recognizing your contribution to the club's success at one of these meetings. You'll also receive an upgraded badge, and if you don't have a badge, then this is a way that you could possibly earn one. And then we're going to start having a volunteer-only gathering in the summer, and I'll share a slide on that a little bit later. Our second tier is a Celestial Navigator. And so for this, you'll need 25 volunteer events. So it's not quite so easy now. Once you reach this level, you'll also be presented with a certificate a badge upgrade, and we'll be tossing back a few ideas, but we also want to give a recognition in form of a gift. So on the MATA side, it'll be a 25 gift card, but we're also mulling over having a more astronomy related item, possibly like a red flashlight or something. And then our final tier is the Cosmic Explorer. And so for this, you'll need 50 volunteer points in order to achieve this level. This counts as a significant contribution to the club. And as such, you're going to receive a very nice plaque, something you'll be very proud to have in your house and hang on your wall. You'll receive the final badge upgrade and a bit of a larger gift. Again, we're thinking around the $50 range, and we'll work out the details of what that might be when we get there. All right, now to honor anyone who helped support this club, we'll be hosting a volunteer dinner. We'll hold it in late April, early May, as that is when the heat comes and our volunteer events usually start dying off. We'll want it to be a little bit different from our Christmas dinner, so no Italian. We're kind of figuring out what we'll serve later on. But right now we're aiming about 5 events per year for you and a loved one to be able to come to this event. And again, this is a pilot, so as we approach, we may modify that. And then for tracking, we want this, of course, to remain transparent. The Office of the Secretary, currently James, will be responsible for managing and tracking and authorizing rewards. The event coordinator in the back and our observatory manager, Claude, will have the primary responsibility for reporting volunteer credit as in the events to the Secretary. But in case they're occupied or anything, then any of the officers or board members can step in. And finally, for those one-off cases, as I mentioned, the board, upon voting, can assign special credits to some volunteer events when that's appropriate. Okay, and that's pretty much the initial take of our volunteer recognition effort. And our goal is that this honors those working for the benefit of our club, but also encourages others to do the same. It's going to be a fresh start. It's going to be, it's kind of like our observing programs that we offer, but just for volunteering. And personally, I can say I came to this club 4 years ago as a member, just sitting in the audience, just like you. And it was last year that I decided to take a more active role in star parties and become a board member. And that's really when a lot of things started blossoming, like friendships with James and Steve and others, and just being more in the community and being able to inspire the younger generation looking through telescopes, and like the joy in their voices when they see Saturn for the first time. And I was like, oh my God, is that real? Can't believe it. All right, but that is it for the prepared material. Yeah. So is there any questions or anything? I did an amazing job then. All right. Oh, we have a question out here? Let the microphone get to you so the people on Zoom can hear you.
So let's say I signed up for one day to volunteer. That's the only day that I'm an operator, but then I come another day. Would that still count?
Yeah, if you're volunteering at Greco, yeah, each time you're there counts as an event.
Thank you.
Yeah. All right, so if you are interested in learning more about volunteering, ask any of us up here and in the back, and we can happy to tell you some opportunities that are available. All right, yeah, thanks.
All right, thank you, Nathan. Appreciate that. James, you're going to be up here in just one moment. So, James, a few weeks back, we went up to the rim, actually about 12 miles or so north of Canyon Woods Lake up there, and had a star party. It was about 20 some of us up there. Great time. James is going to talk a little bit about that. I can do that.
So yeah, that's why he's bringing that up. This was a 4-night event that we had. The first couple nights we had about 26 or so people attending, and then it dropped down from there. So thank you. Before we get into those details, so you can see where from our website that you can get to. Oh, I gotta share the screen. Let's see if I can figure out how to do that. There it is. Okay,
Just share screen one.
perfect.
Share.
All right, thank you. Yeah. So typically you can get to my website through the Astronomy Club on the link on the rental or the purchasing page. I'm going to take you there directly. So hold on a second. Let me pull that up. So the website's www.artscentrics.com, centered around the arts. We just recently did this page. So like I was saying, what happens if you go to the EVAC website, you'll go and get to either the sales page or the rental page, EVAC sales. And here's sales. So before we get into the Star Party, let me show you some about I wanted to point out one of the items we have for sale by one of our members. It's a great deal if you don't have a 6-inch or 8-inch telescope. This thing typically sells for $2,400 and he's selling for $600. Actually, it's like $1,500, but he's got a lot of equipment that goes with it. And I helped him figure out to buy this equipment, and I know he hasn't used it a lot. So anyway, if you guys are interested in buying a good telescope, this is a great one that should last you a long time. So this is a website for sales equipment for the members. We also have equipment that we're selling here through EVAC ourselves. And here's the equipment there that we've got some equipment that's on sale there also. So we got the sales also. Why we're here and talking about it, the Beginner's Guide to Small Telescopes, that's the class that we mentioned earlier. If you're interested in knowing what material is covered, all the material is here on the website. You can just download the PDF thing and you can see exactly what we'll cover. We also actually record the meetings and you can watch some of the meetings on that too. The cost of the class is going to be $20 for members and $25 for non-EVAC members, which is a steal. Obviously, if you're getting five labs and 5 Zoom meetings out of it. All right, all that being said, let's go to the Star Party, if I can remember where that's at. EVAC Star Party there. So it was 4 nights. It was $20 for members, 25 or 30 for non-members. And we did serve dinner and breakfast every meal. We'll probably change that just to one dinner and breakfast is going forward. It's a pretty good size of ranch. It's 20 acres, but there's only about enough space for 25 astronomers. So that will be limited and we'll announce that pretty early on. So if you want to get in on it, you'll want to make reservations early on that because it's going to be a limited number of people on there. It's very dark skies. It's Bordeaux 2 skies. You can see how we had set up here and everything. We also had some astrophotographers up there, and these are some of the images that they took while they're at the Star Party. Like I said, we have some very good astrophotographers in the club here. So it was all in all a really good event. I think everyone enjoyed it. The skies really cooperated with us and everything. And we appreciate Jerry Hyman, who made the ranch available to us. It's his family's ranch, and he just let us use that for the four nights. So any questions about anything I discussed here? So keep an eye open for it next year. We're going to probably do it as a yearly event, but again, it's a limited number of people that can do it. And we're probably going to do it on weeknights to avoid cars coming down the road, because that was the other disadvantage. Is it's a very dusty road and our telescopes are set up right next to it. During the weeknights, nobody comes down, but on the weekends, there's RVs out there and stuff like that. So any other questions? Okay, thank you.
All right. I just wanted to publicly thank James for setting that Star Party up and for actually sort of managing it while I was up there. For those of us that were there, we were all very impressed with what James did. He worked hard up there. Matter of fact, he went up a day early and moved rocks out of the viewing area for hours. So because we had about a 30 by 30 foot area there, but it was quite rocky. And he literally spent, what, 4 or 5 hours out there, I think, moving rocks, something like that. So anyway, the guys that were up there absolutely insisted Did James get a gift card as well? So anyway, there you go. So anyway,
Thanks for coming, everybody, tonight. I want to introduce our speaker, Dr. Russ Genet, who is coming down here from Payson, where he's the current STEM director for the community college system there. And well, Russ has done a lot of things, including on his 84th birthday, getting his float plane rating in Alaska, which is pretty cool. Oh, where was that 64? 84. 84. So Russ has been automating telescope systems before any of us probably had a telescope, including networks of telescopes. And Russ has had his hand in a lot of different aspects of astronomy, published a lot of books on telescope automation and photometry. And he's going to speak about Speckle interferometry, and hopefully he'll explain to you what that is tonight. I had the privilege of working with Russ at Lowell Discovery Telescope and seeing how he does Speckle interferometry. And I think he's going to talk about the work that he does with student groups at Mount Wilson Observatory. So let's give Russ a big hand.
Thank you, Woody. Appreciate that. And Woody, if you would give me the timing, so he's going to keep me from running over. I tend to get carried away. So now I just need to figure out how to. Oh. Here we go. Okay. So I'm going to talk tonight about speckle interferometry, and it's a fancy name, and I'll explain what it is as we go. But first, let me give you a little outline. So I'm going to talk a little bit about my background, just as give a little setting for things. Then I want to talk about binary stars in general. I want a little, particular kind of a little history of binary stars. And then I want to talk about kind of the classical astrometry. Now, it's confusing. You have the field of astronomy, and within the field of astronomy, you have specialties like spectroscopy, photometry, and then you have astrometry, and it sounds like astronomy. It's very confusing, but astrometry, you got the metry there, so it's kind of metering, and so it's really kind of the geometry. It's taking a look at objects in the sky and how they move and where they are in relation to each other. So it's kind of the geometry of astronomy. And so we're going to look at a kind of classic that's seeing limited, and then we're going to look at modern diffraction limited astronomy, and that's particularly speckle interferometry. And so we're going to talk about that. And I'm talking a little bit about the science we do and following up on Gaia. And then at the end, I've got a 4-minute video, and the sound turns out it's not working on this, so I'll just narrate the video. Okay, so a little bit on my background. My PhD is in astronomy, but my bachelor's degree is in electrical engineering. And I spent a quarter century with the Air Force as a research and development supervisor, primarily on rocket guidance systems and also on developing flight simulators for fighter pilots, and even got a little backseat time in an F-16. I am a pilot, and I'm still instrument rated and active in flying. Like that. Okay. I thought I'm so loud, you know. Okay, thanks, Woody. So while I was in my regular working career, I picked up astronomy as a hobby, and I was interested in actually doing some science. So I had looked around, you know, what are the kind of published science things you can do in your backyard on a pretty limited budget, and astronomy was one. There's other fields, you know, you could do bird watching or things like that. So there's various areas that you can actually do scientific research, but astronomy looked particularly attractive to me. And So I built a telescope, and this was back in the late 1970s, and equipped it with a photoelectric photometer to measure the brightness variations of stars, like pulsating stars, eclipsing binaries, and things like that. And I got interested in, maybe starting computerized things. And so I bought one of the first microcomputers that you could buy. There's, at the time, you could get an Apple One or a Radio Shack TRS-80. So how many have heard of the Trash 80? Oh, wow. I've never seen so many. Is the membership getting older? At any rate, on the right there, this is a full page ad in Scientific American. And this is my backyard observatory. And they were grateful that I'd send them saying, how much I liked the computer and how well it was doing for data reduction and so forth. And they sent me a floppy disk drive. And compared to loading it from a cassette tape, that was really good. At any rate, but that was back in Ohio. Decided the weather wasn't really good there, so on my Air Force job, I talked them into sending me out to Williams Air Force Base, where they had a laboratory for developing flight simulators. And so I headed up a branch developing network flight simulators for F-16s. That was a fun job, and I retired from that. And at any rate, while I was out here, I moved my telescope from Ohio out to Arizona, and up in the upper right there, that's myself and Lewis Boyd, who was my partner, another double E. And that was a telescope I brought out from Ohio. And that's down at Mount Hopkins, which has been there. Up behind us, up on the top of the hill, that's the MMT, which back in those days actually was multiple mirrors. And at any rate, we totally automated telescopes, and then we automated the observatory. It was the first automated observatory like this with multiple telescopes. And the lower right there, that was the observatory. You can see four 32-inch telescopes in the foreground, and then the smaller telescopes in the background. And it took us a while, but we got it, so it was totally automatic. You could, it ran itself. We would come down every once in a while, just every few weeks, and check on things. But it didn't always work right. I mean, we got a call one time from one of the day workers, and they said, I was driving by your observatory, and the roof rolled off. The roof rolled back on, the roof rolled off, the roof. The computers do have their problems. And and other times we would worry kind of, how's the observatory doing? Of course, this is way before the internet. And so we would call down to the night operators on the bigger telescopes there, and would you mind going up and checking and looking on the monitors, are things still alive up there? And so at any rate, we finally instituted so that, like say, this was before the internet, but we had it where every morning after things were shut down, it would place a call over a modem and to our computer, so it would give us a log of what happened, did things. And we had weather sensors, so usually that worked pretty well. But one time we had, came back, it was clear, but it was no clouds, but the rain sensor said it was raining. We thought, well, that's a little strange. So we said, well, we'll see what happens the next night. Same thing the next night. And so we called up the observers, and they said, no, it's been perfectly clear. And so we go down and look, and some bird had come along, done a thing to the rain sensor. At any rate, that was lots of fun. So the observatory up there, one of the telescopes they were talking, I got interested in essentially the question, could we have a network of robotic telescopes around the planet to keep things under observation. And could we observe a transit of a planet in front of a star, an exoplanet in front of a star? Because this was back in the late 80s, early 90s. And so I teamed up with Bill Barucki, who did eventually the Kepler. At any rate, we worked through the math and the possibility of doing it. And one of the telescopes actually observed the first exoplanet transit, one of the telescopes we built. It was followed shortly by the Hubble Space Telescope. They got on it. And so usually when you see the first light curve of an exoplanet transit, it's this beautiful one by the Hubble telescope. But this is the actual first light curve, and it was setting in the west. So we only got the ingress on it before it was gone. Anyway, that was fun. This is Alex Filipenko. We built one of it's the same telescope you saw. We built one for him, and it's been operating up at the Lick Observatory at under the Kate Dome there for, well, it started operation there in the late 90s, so it's been a little over a quarter century. But Alex came to some of my meetings, and when he graduated from Berkeley, he got a Presidential Young Investigator Award, and he used that money to purchase a robotic telescope from us. And it did discover, what it did, it observed quite a few hundred galaxies every night looking for new supernovas. And so it had a record for most supernovas discovered for a number of years. And Alex was particularly interested in the type 1A supernova. And so this was in the late 90s, and they used that for calibrating the real distant ones. Another thing I got interested in was making smaller telescopes, smaller research telescopes. So we have a group called the Altaz Initiative. And one of the things, we went around and visited large mountaintop telescopes, talked to the engineers, the observatory director and so forth, and would ask them, how can we capture some of these things that you're doing and do them on a small scale with smaller telescopes. So that's the Gemini telescope down at the CAS focus there. This is the Subaru telescope up on Mauna Kea, which uses what's called direct drive. And so we ended up, and this, in the lower left there, that's some of my students when I was at Cal Poly in San Luis Obispo. Anyway, we had a couple of student teams. We built the telescope in the upper right there, and it was the first kind of small telescope that used direct drive. And the upper left there is our first direct drive motor. Actually, it's used to have magnets and coils. We mounted this on plywood to test it out. And the lower right there is a machine version. At any rate, this caught the attention of the plane wave instruments. They were involved. Dave Rowe was part of our project at Cal Poly. And this resulted in the first, so plane wave up to that point had just made the optical tube assemblies, OTAs. And they decided to start building complete research telescopes. So they use the technology that our students at Cal Poly had developed. And the plane wave's gone on to make lots of really nice research telescopes. And Woody has one of them. Is there any other club members that have plane wave telescopes? Yeah, how many want one? Okay, so now let me talk a little bit about binary stars. So I want to do it a little bit from a historical viewpoint. So if you go back to the Greeks had thought both about a heliocentric models for the universe and Earth-centered models, geocentric models. And they knew if the Earth went around the sun, you would expect, as shown in this diagram here, that if you had some bright nearby star, as the Earth goes around the sun, every 6 months, the brighter nearby star should shift with respect to a faint background star as you go back and forth. Well, they looked at it and then they couldn't observe it. They couldn't see any shift. So it was really only two conclusions. So either the Earth was really the center of the universe, or the stars had to be an awfully long ways away. But there were other reasons that they thought maybe the Earth was the center. And but that's the early interest in binary stars. A bright star and real close to it is a faint star, and you're looking to see if over the 6 months they do this. And they couldn't see it. So Kepler, who was very interested in this and thought that the sun was really the center of the solar system, he asked Galileo to take his telescope, which he just started using, and look at some double stars over time and see if he could see a faint star and a bright star shifting back and forth, suggesting, and that way they would get some idea of the distance. Well, Galileo looked and he couldn't see any. And but he did have the first report on telescopic observations of binary stars. Well, to make a long story short, it was quite some time before telescopes were powerful enough to detect this small shift. So this is William Herschel and his sister Carolyn. And so he's in 1781, he started surveying the sky looking for double stars, particularly pairs that are bright and faint. And he started recording their position with respect to celestial north and how far apart they were. And so what he expected to see was their separation, how far apart they were, they change over 6 months. And so just a couple of years into his program, as he surveyed the whole sky looking for double stars, what did he find? Anybody? What did William Herschel discover? I heard Neptune. That's not right. Yes. Yes, Uranus. So he's the first person to discover a new planet. And he did this while he was looking for double stars. Well, the interesting thing was that after 25 years of observing lots and lots of double stars, he concluded that he couldn't find the shift like this. But what he did find, that the faint star in relation to the bright star was going on an arc. And so he made the conclusion that these had to be gravitationally bound. Prior to then, they thought all stars were about the same brightness, but this showed two things. One, that Newton's law of gravitation was a universal, it applied to the stars out there, and that these binary stars could be way different in brightness, but actually at the same distance and revolving around each other. So and he coined the term binaries. So we thank that William Herschel for that. Now, if you have a binary star in an elliptical orbit, and face on it may look like this, but from Earth, it can be tilted and up at an angle. So we call this the apparent orbit of a binary star. Yes, and so this is an actual orbit of a binary star, and I've tilted it over on the side so the north is along the x-axis here. And you can see up there, see the east and north. So the star is going to go around this orbit. This is an ellipse. And each one of these points, and we'll talk a little more about that, is an observation. And but the key point here is this is an elliptical orbit that's been tilted, and then we're seeing it from the line of sight from Earth. Okay, and so Kepler's first law of his three laws is just that planets follow an ellipse with the sun at one of the focal points. And this shows how you can use a couple tacks and a piece of string and a pencil to draw any ellipse. And this is the only math in here. So up at the top is kind of the standard equation for an ellipse where A and B. A is the what's called the semi-major axis. That's the long axis of the ellipse, and B is the short one. So if it's a circle, they'll both be the same. But as it gets long and elongated out, then the semi-major axis is longer than semi-minor axis. But when you tilt it and you rotate it and you translate it, that adds in other terms. And so that's the equations down below. But we'll go by them quickly, and we'll skip any of the differential equations. Okay, so Kepler's second law is that a planet going around the sun, and this actually applies to two stars too, sweeps out equal areas in equal time. So let's see if we can, so let's say this is moving around in this direction here, and oh, you can't see the, oh, well, I'll just show it up here. Okay, so let's say that's the sun, this is a planet, and the planet's going around, and it's going slowly here, but it's got lots more area. It's just further out. When it comes around here, it speeds up and kind of whips around here and then slows down. But what Kepler found was that this area A was equal to this area B, which is, you wouldn't really expect that. And that was an important discovery. And what that allows us to do is that, so I was talking about how the ellipse can be tilted with respect to the line of sight from Earth. This additional information by having the equal areas swept out in equal time, this allows you to then solve mathematically for the orbit. And so the first person to do that was William Herschel's son, Sir John Herschel. And he went to Cape Town, South Africa, where he set up an observatory to observe double stars like his father did, and also look for galaxies. How are we doing, Woody? 25 to go. Okay, no problem, we're good. And he figured out how to analytically solve for these orbits as you would see them face on. And it's a pretty nasty math problem. It's called, uses Kepler's equations, and it uses Newton's method to solve the equations. So going back to here, I want to point out, so once you've calculated an orbit, now it may or may not be the right orbit, you calculate an orbit, then you can take an observation. So let's take this one right here. So what this is, so this point here, that green cross, it's the distance. So this is the position of the bright star. This one's going around in this direction. And so this green spot here, it's coming around here. And this was the reported observation. And they reported this distance here. It's called the separation. So if we do that, we look down here on the scale, that's about something less than 2/10 of an arc second. And this is tied into, and it's also got an angle with respect to north. So here, north is out that way. East is at 90 degrees. This would be what, 135, 145, anyway. So that's an angle. And then it's also a time. So as the thing goes around the orbit, it's various measured or predicted times. And this dashed line here is connecting this with the time on the orbit. At any rate, This is getting a little technical, but we'll move on to less technical things here. Okay, Kepler's third law, he realized that when he looked at the data, that the square of the orbital period in years was proportional to the cube of the semi-major axis in the astronomical units. And you can see they just plot on a nice straight line. And so what this means is that, well, we did have one more formula. The square of the period is proportional to the cube of the separation between two of the semi-major axis along the ellipse. And the proportionality constant is 4 pi squared over g. This is what Newton came up with his universal law of gravitation. And m1 plus m2, that's the sum of the masses of the two objects. And so what we can do then with double stars, the semi-major axis, when we look at it on a plot, that was an angle really, an angle in a star. But if we know how far away it is with parallax, then we can convert that to an actual unit. And if we we'll know the sum of the two masses, then if we have some way of parsing this out to individual masses, then we've come up with this really important thing. We can know what the mass of each star is. Now, it turns out this is the best way, the most accurate way to determine stellar mass. So that's why this whole thing with binary star research is a really big deal. And so we're just figuring out the period and the semi-major axis. And then with a little bit more of astronomy, we get the individual masses. And individual masses are really a big deal in astronomy because faint stars, less massive stars, they really evolve slowly. So here we have stars coming in, what's called a zero main sequence. And heavy stars just zip in thousands of years. Really lightweight stars, they can take billions of years to get to the main sequence. Okay. And this is the HR diagram that probably most of you are familiar with. So mass just is a very key thing for our stellar models and understanding things. And that's the whole reason that we really care lots about binary stars. Okay, so now how do we observe the binary stars? And the classic observations, most have been made with refractors. On the left, there's the 36-inch refractor at Lick Observatory. And on the lower right is what's called a filar micrometer. And essentially, it's got a high power eyepiece, and you can see the knobs on it, and it's got a crosshair and a fixed crosshair and a movable crosshair. And you rotate this whole thing around, and there's a vernier to read off the angle. You rotate it around until the two stars are lined up along a horizontal crosshair. You put the vertical crosshair on the brighter star, and then the movable crosshair, you crank the micrometer screw, move it over, you measure, you read off the measurement, how far they are apart. So that's the separation. And you then read off the angle, and that's the angle with respect to north. And so now there's three things that you report. You report how far apart they are, you report the position angle with respect to celestial north, and when the observation was made. Usually just the date is sufficient. And so then that makes one of the points. And so that diagram we showed there where there was maybe 50, 60 points, that's 50 or 60 different astronomers at different times went out to their telescope, made this measurement, and got it published in a paper. And so this goes, it's been going on for well over 200 years now. So so double star astrometry is a very cooperative, intergenerational endeavor. So I think I've shown enough on this, so I don't have anything more to say on that one yet. Okay, so now another way of making the measurements, and one that doesn't require a 36-inch reflector or one of the really expensive filar micrometers, is to use what's called an astrometric eyepiece. And so this eyepiece, essentially, it just projects a ruler on the sky and a protractor. And you use the ruler to measure how far apart the two stars are. And you turn the drive on your telescope off, and it will, of course, drift off. The Earth is turning to the west, so this will move this off, and you can turn the drive on when the star reaches, the binary star reaches the protractor, and you read the angle off. And so now you've got you've got the separation, you've got the position angle, the date you're at it, and so you can observe one or more of these, write it up in a paper. Here's how we did it, and report it. And you've got it's added a point to the thing, and if it's the students, the students get a published paper. And so we started doing this. We actually started it out at the Apache Junction campus of Central Arizona College in 2001. We had our first seminar, but me and my wife moved to San Luis Obispo very shortly after that. So we started up a class there at Cuesta College, and that's all students from Cuesta College, and we had dozens of published papers. At the time, I think it was the high school. So it was high school students signed up for the community college, but they were essentially all high school students. We held the class, high school campus. And so we claimed that it had the most published papers of any high school in the United States. It may still hold the record. It wouldn't surprise me. And it was slow to start the first year, but once the word got around that, the students with published papers were getting scholarships, admissions to college and so forth, it took off, and it always filled up. As soon as the class opened, it would hopefully fill up shortly. It was really worked well. And we spread out. We just started doing the summer camps where we would have students come in and make observations and write up their papers. We'd edit them. They rewrite them. I'm sure you're getting into that, right? Writing and rewriting. Yeah. And an offer for publication. Anyway, that worked well. And this was the start of it down in the San Diego area. This was an Army and Navy Academy right on the coast. And it grew. So there's now 4 or 5 community colleges there, and a number of high schools, occasional students from San Diego State. At any rate, they have 2 robotic telescopes now, and they have at least 50 published student papers. I mean, one of their students, community college student, had a paper on using AI to identify double stars that it got published in the Astronomical Journal. That's just, at any rate. Okay, so that's kind of classic ways of observing binary stars. So I want to talk now. Yes, how are we doing? Okay, we're good. Famous last words. So I want to talk about how we do binary star observation now. The problem with binary star observations is, it's one thing, you really need to get the radial velocities to split that combined mass into individual masses. And but to measure the radial velocities, if it's really widely separated and easy to see with astrometry, it means that that star going around is going really slowly. And so its radial velocity is slow. It's hard to measure. It's down in the noise, particularly back, if you go back, quite a few decades. And on the other hand, if it's a short period and it's moving fast and it's easy to measure, that means short period means that it's going to be in real close. And so, you're kind of between a rock and a hard place. If it's fast, you can get the radial velocity, but you can't get the astrometric separation. If it's slow, you can get those, but you can't get the radial velocity. And to make things worse, the stars, so if nearby a star has this separation, if you move out, as you go out, the apparent separation, of course, gets smaller and smaller. And at some point, it's not measurable at all. So the problem was that this seeing limits how, just this, the atmospheric interference smears out the image. And so, if you have a scene, so what's typical scene here? Okay, 3 arc seconds. So 3 arc second separation for a binary star, that's pretty wide. It's going to be really slow. And so there just weren't very many stars where you get the orbit and the radial velocity, and that way get the individual masses. So the whole problem with this was the seeing. We were limited by seeing. And what happens, you get the light emitted by a pair of binary stars, way far away, and the wave coming from them stays just perfectly nice and playing in parallel all the way till it gets to the Earth's atmosphere. And then it gets stirred up in this last little part of the journey, and we get these perturbed waves. And so here's what it actually looks like at on the telescope. Now, you'll notice there's a bunch of things that kind of look like speckles. So this is where speckle interferometry. So this is a whole bunch of short exposures, just one after the other. Let me show it one more time here. Up. So it's moving around this way, and the pattern is constantly changing, and that's speckles. But if you take short exposures, you freeze out the motion. It's just that it's jumbled up, but the information is all there, but it's jumbled. But each time you take it, it moves around and it's changing like that. So over in the upper left there, that's Antoine Labouré. So he's a French astronomer, and he realized, let's just take a bunch of short exposures and then we'll combine them together and do a little processing. He actually used, so up in the upper right there, this was some series image intensifiers and a high-speed film camera, and they put it on the 200-inch telescope at Palomar, and they were able to overcome the seeing limit. Well, the seeing limit's really critical. No matter how large your telescope is, if you aren't doing something to overcome the seeing limit, you can't do better than the resolution of an 8-inch telescope. So that's just due to that, because that's about the size of the air cells in the atmosphere. And so this turned out to be a very big deal. And Hal McAllister in the upper right there, as a postdoc at Kitt Peak, he realized that if he did speckle interferometry on the 4-meter telescope shown there on the left and the 2.1-meter telescope at Kitt Peak shown in the middle right, that with speckle interferometry, he could measure them really close, and the radial velocities would be measurable. In fact, we're already measured on a bunch of these. They just needed the astrometry. They needed the orbits. So he started, and he really cleaned up. So this he became very famous, became his career, became the chair of the astronomy department at Georgia State University, and just went on to fame. And originally they used high-speed tri-X film, actually got in a cascade and strapped themselves in to operate the system as the telescope moved around and took the film that way. But it wasn't long before they started using an image intensifier. So this is the nearby wind telescope doing speckle interferometry. That's in the middle there. That's with Elliot Hort. So I'm with a run on him on the wind telescope. And this is the Gemini telescope. And so this is Gemini North, and they have permanently built into it, and Gemini South a speckle interferometer camera that they use. And so this is kind of the ultimate of speckle interferometry these days. Well, so what I want to do now is talk about what amateurs can do in speckle interferometry on small telescopes. So upper there, that's Florent Loss, a French amateur astronomer. He built, that's a 16-inch telescope that he built. And you can see the little red camera. This is a fairly early CCD camera. And the CCD cameras, if they don't read out very fast, they're slow. So if you're trying to take 1,020 millisecond exposures, you'll spend 2 minutes total taking it out, but an hour reading it out. And but he kept at it and was producing really good results. Very impressive results. I met him in person down below there. He's on the right, and this was a double star conference in Barcelona. At any rate, so I really got interested in, maybe we could do it. So here I'm at the Cascade on the 4 meter. Now, instead of a film camera, this is an intensified CCD for fast readout. And in the middle there, that's Brian Mason from the U.S. Naval Observatory. And on the right is Joe Johnson, one of my star students. At any rate, we got intrigued. And so I managed to get what's called an electron multiplying CCD camera. So in the regular CCD cameras, you just read them out. The electron multiplying, they have an extra row as they're reading things out. They put a fairly high voltage between each of the pixels. So when the charge from one pixel goes to the next, it knocks out more electrons. That knocks out even more. So it's kind of like a photomultiplier. And you start out with a small signal, you get a large one. That way you can read it out fast, and so it overcomes the noise. And but they were very expensive. That was a $14,000 camera. And so this is at my observatory before I moved it from California. There's a couple visiting astronomers from China there, and another one of my star students on the left. And this, you'll recognize, there you are, Bob. Yeah. So tell us, give us the 30-second remembrance of that.
Well, this was at, if you know Dave Rowe of Plane Wave Instruments, this was at his observatory. And I don't remember the student at UCS. Eric Weiss. So Russ organized sort of a production line where everybody had a job. One person was controlling the telescope, one person controlling the camera, the next person picking the target, and somebody else processing the results from the prior target. So you can work your way through a lot of objects and come out with position angle and separation measurements, bang, bang, bang. And the cycle is rapid because of that electron multiplying CCD. You get 20 millisecond images coming down just like a movie. So it's a fabulous experience, except it was cold.
It was the desert. We usually go out twice a year. Dave Rowe, it's actually officially the Pinot Valley Observatory, but we just call it Rowville. Right. So, and I spend every winter in Hawaii. This is going to be I think our 20th winter. We're leaving the end of November. And this is Leeward Community College, and it's right on Pearl Harbor, as you can see. You can see the ships out there. And there's the camera on their half-meter telescope there. We did, and the students from the community college and the local high school had published papers. And here we are over on Haleakala. So this is the 2-meter Fox North telescope. There you can see the camera on one of the ports. And we left it there a week, and it was cloudy all week. We never got any observation. That was very disappointing. This is Kidd Peak National Observatory. This is a 2.1-meter telescope. And again, you can see the camera. It's totally dwarfed, but there's our camera. And it was, state-of-the-art camera, actually on an old telescope. This is Kent Clark, believe it or not, is his name. He was the editor of the journal Double Star Observation many years. So we invited quite a few people for the run. There's students there. You can see the camera again at the bottom of the telescope. There's the students operating the telescope, and Richard Harshaw is in there. There you can see him bottom left. So he's a member of your club, is that right? He was. Well, if he isn't now, well, he got married again. So here's. This is hard. This is the 100-inch telescope on Mount Wilson. It's a little hard to see, but the camera's right up there. That white tube is actually a feed of the image from the 100-inch mirror down. This is, well, then there was a revolution. So this is a big deal. The first CMOS camera. So that one on the bottom of the telescope, that's my wife, Cheryl. And that's my telescope in California before we moved. But you can see the typical ZWO camera there. That was one of the very first ones that they made. And it was like $400. I mean, compared to 14,000, it was lighter. It wasn't sensitive. The EMCCD cameras, if you overexpose them, you could ruin them. There was lots of problems. Anyway, it just totally revolutionized speckle interferometry and high speed, and lots of other good things to say about CMOS cameras. This is the ELSOS Observatory down in the Chilean desert, not far from CTO. So this is the Atacama Desert, and we do automated speckled interferometry on a 1-meter telescope down there, and we do lots on Mount Wilson. On the left there is Tom Meneghini, who's the current director of the Mount Wilson Observatory. On the right is one of the students. He's about to put a CMOS camera there. This is not this June, but the previous June, operating the 60-inch LEDs. We actually sit under the dome with all our computers and so forth. And the telescope's still manually controlled. So we control the computer and the focus and everything from our computers, but then we write the coordinates down of the next target to observe, and that's handed to the telescope operator. And so then this past June, so just a few months ago, we put a CMOS camera on the 100-inch telescope doing speckle interferometry, and there's our group on the 100-inch telescope. How we doing, Woody? Okay, good. And here's a great story on cameras. So this is the CWO ASI 462. That shows the quantum efficiency curve. And the big deal here is when you get out into the near infrared. So we're past the visible, we're getting into the near IR. So here's out at 1 micron, but the efficiency is still quite good. And so this camera is so good that the Andre Tokovinen, who's the speckle interferometry expert in Chile on the SOAR 4.1-meter telescope, they had an $80,000 Andor Ixon camera. He's replaced it with this ZWO camera, and it costs $250. That's really amazing. So here's the current, this is what we've been developed up in Payson. There's the 462 camera. So this is on the back of just a small telescope. Here's a flip mirror that's all computer controlled. You can either come back here. Here's a full frame ZWO ASI 2600, or you can flip it to the science camera. We've got the filter wheel has the full 2-inch ZWO Sloan filters. That's the motor to flip the mirror, and this is power and so forth. Anyway, that's our latest camera for Speckle interferometry. And there's a before and after up at my observatory in Payson. You can see I'm a little bit sky and tree limited, but it's got a flip top roof. And I'm going to go through this quickly. So just want to tell you a little bit how we do analysis. The Renaissance genius Dave Rowe wrote our software. It's quite friendly, runs on a PC. So that's an image. You can see the bright star and the faint star there. And you can see right down to the pixels. So we're measuring small separations. We like small separations. They're small, short periods, and so here's a. So this was the last observation in 2005. These blue ones are speckle interferometry. These green crosses, those are all visual. You can see how much more accurate the speckle interferometry is. And since this was published, it's covered up here, but there was another one here. This is Tokavinen down at the 4.1 meter SOAR telescope in 2018. This is him in 2021. This is us students observing the Mount Wilson 60-inch. Not this past June, but June 2023. So you look at this orbit and you say, well, the orbit that they published, but here, it's pretty good up to there. But if you look here, it's going off track, isn't it? And we verified that, not only Tokavinen shows it, but we show it going off track. So you can compute a new orbit. And there's the new orbit. And it's also an ellipse. You just change the parameters like the major axis and the semi-major and the semi-minor axis and the inclination, things like that. And Dave Rowe wrote a program called Orbits that we can then get all the coefficients. So down below there, this is what you publish. If you know these values, that tells you the orbit. And if you know that's the apparent orbit, if you know how far away it is, then you can get the actual orbit. And if you do some radial velocities, you can split the mass from Kepler's third law into the individual masses. Okay, and how are we doing on time now, Wade? Close out. Okay, we're close to being finished. So what we're doing now currently, we're doing follow-up observations to Gaia. So that's the European Space Agency put this telescope up in 2013, started observations in 2014. It does astrometry. So it's the world's best astrometric telescope out in space. Absolutely amazing work. This is that gray part is called the Gaia hole. It can't observe stars in this area. I won't go into the details of why, but we can from the ground, and we're doing that. So we're doing things that Gaia can't do, and we follow up on what Gaia does. Here's Andrei Tokavinen. On the left is the 4.1 meter SOAR telescope out of the Atacama Desert in Chile. And he's been observing what are already known to be binary stars, with two stars in this elliptical orbit. And what he's doing, he's looking at each of the components because he thinks Gaia has given us a hint that one of those two stars has an additional one, which makes it a triplet. And that's really valuable because it helps us understand how do stars form to begin with. So these doubles, triples, quadruple stars, so forth, tell us lots about stellar formation. And this last week, Woody joined us this is the 4.3 meter Lowell Discovery Telescope north of Payson. It's between Payson and Flagstaff, so it's not far. The engineer that runs it actually commutes from Payson. And there we are. This is down at the business end. Woody, you're a little bit in the, well, no. See, you got a white hat there. And any rate, this is, and here we're, so we actually took one of Tocqueville. So the SOAR telescope in Chile can only observe so far north. And so beyond that, Andre couldn't observe. So we asked Andre, maybe we could observe some of these for you. So we're going to do that at the 100-inch in Mount Wilson. But this in the middle there, this is Gerard Van Bell. So he's the science director at Lowell Observatory, and they had a remote person observing, and we asked for, could we observe one and of Andre Tocqueville's northern binaries, and they put it. Did you select it, Woody? We were looking there. One of us said, well, maybe this one off the list. We were looking, I guess, at the RN deck. This would be a convenient place in the sky. Anyway, we observed it, and there was a third star. So it was a triple star discovery. So it was high fives, wasn't it? Okay, so this is the last thing I want to show, a 4-minute video, and I'll narrate it. So I know we're kind of out of time. Now, where will it be? Oh, Steve knows. Stop sharing, Tom. Yeah, share.
Sciences Symposium and conducted observations using.
Okay. So
In
there's
June of
dramatic music
2024,
and
a dedicated group of students, educators, and amateur
full
astronomers
screen here.
took part in the Society for
how do I
Astronomical
get full
Sciences
screen?
Symposium and conducted
I
observations
see it. Yeah, there
using
we
the
go.
100-inch and
Okay,
60-inch
so dramatic
telescopes
music
at the Mount
saying that
Wilson Observatory.
students
Here is a glimpse into
Society of
that week.
Astronomical Science, Bob Buckheim is the president. And so here we are and giving talks. And we're talking about binary stars, and the students really love SAS. That's a really good experience for them. And so if you haven't been, do come to Ontario towards the end of June every year. And so that's the team from Colorado Mountain College. So then this immediately afterwards, we head up to Mount Wilson, and that's the monastery there. There's the students in K. That's the 60-inch telescope. Okay, we're heading up the stairs. Okay, there's the 60-inch telescope built in 1907. Still works very nice. That's the 100-inch telescope. The stairs are a little bit longer going up there. And we're going to do Speckle. So this was just this past June. And we're going to do Speckle. There you can see the refractor tube coming down there with the, there's our camera that we put on it. And then we visit the char array, which is 1 meter telescope spread out, and it gives it the resolution. Like telescope was like a quarter, half a mile in diameter. The opening, the slit, we park the dome to the south and catch the stars as they go by. The dome is pretty slow operating. There's operating at night. classic operating stations are Hubble that operate the telescope, like we've added the computers. We can see Speckle. So this is checking stuff out back in the day, but still on the 16-inch. And it's moving. You see, that's a 16-inch going rotating. Okay, it's moving already. Big worm deer. Nice food. Mount Wilson is just a lovely place. Students love it. This is the dining room. This is in there's a chair that's where Einstein sits. So the students love to sit in the chair and get a picture thing. Now this is the chair with Einstein to that. And that's the walkway there. Where we are. That walking on the anyway, we do that every year. Okay, that's it.
Well, let's thank Russ for coming down here and talking to us about Speckle. And Russ loves questions. Do we have any? Ah, good, we got questions. And she's a physicist.
What's Speckle interferometry?
That's a good question. So speckles are those things that we saw around. So that's the speckles. Interferometry essentially means interference between two things, and it's this interference that allows us to kind of reconstruct the image. It's a little bit of a misnomer, but it's close.
So many different places around the world and so many different sized telescopes. Is there like a central repository of where this information is going into and out of so that you guys can kind of coordinate and see what's being done and
Absolutely.
intermediate objectives?
Yes. So as you can imagine, this is really a thing that goes over decades and even centuries to get slow moving. One may not have even over 2 centuries may not have completed an orbit. So the U.S. Naval Observatory quite some time ago volunteered to keep track of all things. And what they do is if your observation is published, so you publish the position angle and the separation and the date of operation, they will include it in the Washington Double Star catalog, starting mainly with William Herschel and his many observations. And so the students, but it has to be published. And so that's the opening for students. So there's a number of entry-level journals like the Journal of Double Star Observation, but there's one in England, there's one in Spain, the Russians have one, where us lower level observers can write up their results, get it published, and then the Washington Double Star picks it up. And when the observations are put in, they put in a 3-letter identifier for the first author. And so if the first author is a student and this is their first paper, they are not only is their data entered in the Washington Double Star catalog, they have an observer code, and you click on the code, there they are. So at any rate, it's forever. Good question.
Okay. So I was curious on the one that you said that the orbit that you all measured and confirmed an orbital change on the binary. Is there any reason why that changed, or is it just that over time that this just sits within kind of that margin of error?
Well, that's a good question. So we saw the one where they had an orbit, it looked solid, but then some later observations showing it was going off. And so as soon as you get enough points that you can get a good guess in the orbit, some astronomer is going to come along and grab credit for publishing the first orbit, okay? But then other astronomers are going to keep observing it, and they'll, if it stays on the original predicted orbit, then they won't publish a new one. But if it's clear it's going off orbit. Now, if it just goes off one time and you publish a new orbit, then they can say, he's published happy, he's trying to get too much easy glory. But if after several observations, it's clear that it's off track, that just means it needs a new orbit.
So interferometry again, the speckle interferometry, you're getting those speckles. There's an interference pattern from the turbulence in the atmosphere. The interferometry part of that is the interference pattern that you get. I guess the rest of it is embedded in the software that you're using to get the correlation you're looking for.
Yeah, so that's a good question. So the software itself, what you actually do is you take, typically you'll have 1,000 images, and you take each image and get a fast Fourier transform of the image. And then, and it turns out, in terms of a whole bunch of Fourier transforms, if you look at all possible separations between all the speckles, there'll be various possibilities. But when you get to the actual separation of the two binaries, there's lots of them. It jumps way up, okay? And so yeah, and then you can actually kind of reconstruct an image of sorts out of that.
Any other questions?
Adaptive optics came around, 25 years ago or so. What kind of an impact does that have on spectral interferometry? I would imagine it's a dramatic one.
That's an excellent question. That's a very, very perceptive question. So it turns out adaptive optics can overcome the seeing limitations in the same sort of way, a different way, but it can also overcome seeing limitations like speckle interferometry can. And adaptive optics can give you the same results as speckle interferometry. So there's advantage and disadvantage to each. The main disadvantage of adaptive optics is normally you need a high power laser to go up and put an artificial star. And then the light comes down and you take off part of the light, put it through what's called a Hartmann mask, and process that information and use that information to deform a secondary or tertiary mirror, usually a tertiary small mirror. And so that's all very expensive. And I think they still require, when you're operating with a high power laser, you have to have a person on site checking for airplanes. And anyway, it's very expensive. Speckle interferometry is much, much cheaper. And you tend to get the same results. So it turns out that for doing binary star research like we're talking about, that the big telescopes and professional astronomers tend to use speckle interferometry as opposed to adaptive optics, which there's other places where only adaptive optics works.
We got one online here. How do you get from the speckles to the final image?
Say again.
How do you get from the speckles to the final image?
That's also a very good question. So there's two ways. One way is called an autocorrellogram. And when you do that, it shows what looks like the primary star, and it shows this secondary star, but there's two of them, one on each side. And it's not really an image. It's a mathematical solution shown in on two space. But there's another way. If you can reconstruct when you do speckle interferometry, you lose the phase information. So that's what the AI question. You don't lose the phase information when you do adaptive optics, because you're actually getting phase information to shape that tertiary mirror at high speed. So but what you can do is, after the fact with speckle interferometry, you can solve for the phase. So you actually do one of these hill climbing routines. And so it's very computer intensive, but the computer's very fast now. And so you can do that. And so when you do that, and it's called bispectrum analysis, you then actually end up with, you reconstruct an actual image, and you can get an image, and you can do photometry on the individual components.
What do you see in terms of Gaia's impact long-term? It's measuring proper motions, it's measuring parallaxes. It's going to hand you all of the orbital information. Is there still room for ground-based?
That's an excellent question. In fact, my first connection with the answer to that, so it must have been 2012, I submitted a proposal to the National Science Foundation to do, these observations. And they went back and says, well, this is a really nice thing, but we think that maybe Gaia is going to take care of this, okay? Well, a few things happen. One is that Gaia gives us, by giving us really good parallax measurements, that means that one of the uncertainties in determining stellar mass has really been reduced. And so that's good news. In terms of discovering new binary stars, it's just, we knew we had orbits for about 3,000 binary stars before Gaia. It's added, I don't know, 100,000 new binaries. It's a huge number. But interestingly enough, most of them are what are called photocenter orbits. And so what this is, it sees it as one star, but it can measure its position so accurately, it gets a measurement of this photocenter moving around. But they don't, in order to get mass and so forth, you actually have now observe it with a telescope that does astrometry. And then I mentioned there's blind spots that it can't do. There's all sorts of follow-up, but like in other areas of astronomy and kind of astronomy through the ages, technology changes. And if you don't pay attention, if you don't stop doing the things you've always done because they've been outdated and do new things that fit in, you aren't really doing science. So anyway, good question. But the answer is it's not putting us out of business. If you do it right, it's new business.
All right, thank you, Russ.
Yeah, you're most welcome.
All right, folks, thank you for being here. Once again, we have our meeting third Friday next month.